Hereby I open this academic ceremony at Maastricht University. My name is Ton de Goeie. I am the pro-rector of the ceremony and chair of the degree committee. First of all, I would like to welcome Mrs. Melania Buonocunto. She will defend her academic thesis, which is entitled Stretching Boundaries, Bridging Mechanical and Electrical Functions of the Heart, a multiscale in silico characterization of the pro-arrhythmic effects of stretch-activated ion channels. That's quite something. Welcome all members of the degree committee, and in particular I would like to welcome the three supervisors sitting in front of me. Professor Joost Lumens, he is professor of computational cardiology at Maastricht University. Professor Jordi Heijman, he is professor of medical physics and biophysics at the Medical University of Graz in Austria. And Professor Tammo Delhaas, he is professor of biomedical engineering at Maastricht University. I will introduce the 6 opponents later during the ceremony, during the opposition. Welcome the audience here in the aula, and I would like to welcome also all followers of the live stream. Mrs. Melania Buonocunto, may I invite you to give a summary of your thesis? I wish you lots of success in the coming hour, and the floor is now yours.
Dear Prorector, dear members of the Defense Committee, supervisors, friends and family, people watching online, thank you for being here today. It is my pleasure to present the content of my PhD thesis in this academic session. So, when we think of a heart, we think of our most important organ. It works tirelessly, pumping blood into our system. But in reality, it is much more complex than that. So every heartbeat is driven by electrical activity, which tells the heart when to contract. And this is how the rhythm is maintained. But actually, the other way around is also possible. So contraction and relaxation of the heart can influence the electrical activity in a process that's called mechanoelectric feedback. And this is part of the normal physiological behavior of the heart. So that's how the rhythm is maintained and the body works. But this is not always the case. Indeed, when external forces come into play, this very delicate balance is disrupted. So let's imagine a baseball player. The ball is coming towards him, and he's ready to swing his bat with full force to hit the ball. So he does that. But the other player who's trying to catch the ball is not ready yet. So the ball hits his chest, and he doesn't get the ball. So after a couple seconds, when nothing is happening, the player collapses. What's going on? Well, let's rewind the scene to understand. So when the ball hit the chest of the player, it actually delivered a perfectly timed and strong mechanical impact directly to its heart. And the heart rhythm was disrupted. So the player, that's why he collapsed. And this is a very rare but dramatic example of a phenomenon called commotio cordis. But commotio cordis does not only happen during baseball. There's many other sports when it's involved. For instance, football, tennis, hockey, or in car crashes, in pathological conditions, or during fights. Sorry. And so what all these players have in common is that they are triggered by mechanical input. That's the expression of the extrinsic mechanoelectric feedback, which provoke disruption in the heart rhythm. And those are called arrhythmias. So those arrhythmias can be really dangerous because they can lead to sudden cardiac arrest. But what happens behind the scene? Well, let's have a look. So the heart is made of layers, and one of them is the cardiac tissue. But the cardiac tissue itself is also made of cells. Those cardiac cells are called cardiomyocytes, and they're able to contract, but also to have electrical activity. The cell is surrounded by cell membrane. and this cell membrane divides the inside from the outside of the cell. And on top of that, there's ion channels. Those channels are gates, and they actually let ions, such as potassium, sodium, calcium, flow in and out from the cell. And actually, this movement of ions, it's what causes electrical activity and currents. So every cell is actually associated with an electrical signal, which is called action potential. And that's given by this beautiful movement of ions, which creates current. And that's what causes cardiomyocyte contraction in a normal way. But as I was explaining before, this rhythm can be disrupted somehow. So that's where those external forces come into play, and other gates also. So there exist some gates, some ion channels, called stretch-activated ion channels. And as the name says, they are directly triggered and open by a mechanical input that stretch the cardiomyocyte over the physiological range. And that provokes new ions coming in the cell or out, so more current. And that actually provokes stretch-triggered action potential, which is a new electrical stimulus, which actually overlaps on the previous normal-paced one. And as you can imagine, that really creates problems. But how? Well, there's many ways of studying that. So one can rely on experimental data, such as animal studies or cellular studies or clinical data. Those can be really useful, obviously, but sometimes they're very challenging to perform or costly, or it's difficult to really dive deep into specific parameters inaccessible, for instance, in clinical studies. So one other way of doing this is using computer models. So that's what I did in chapter 2 of this thesis. Using the available experimental data, I developed simulation of a human cell from left ventricle, and I created a computer model of a cardiomyocyte to explore what's the impact of this mechanical external force, implementing those stretch-activated channels. And we found out in chapter 2 that the wrong combination of conditions related to this mechanical force, such as the strength, but also the duration and the timing of this impact, they can stretch-induced arrhythmias in cell, creating this disruption of the normal heart rhythm in the cardiomyocyte. But what happened in tissue? That's another question I asked. So, as I was explaining, cardiac tissue is made of cells, interconnected to each other through something called gap junctions. And these are important because they really can let those ions that are produced in a cell flow to the other neighboring cell. So let's imagine a grid of those cells interconnected to form a tissue, simulated tissue. And each cell still functions electrically, so there's an action potential generated by each of these cells. But those cells can be in different states. So for instance, they can be in resting state, as this purple color means. That means that they are ready to receive another electrical stimulus. So let's give it to the tissue. A new electrical stimulus activate, that's the red color, the first column of this grid. That means that the action potential starts to be produced in that column. And as I was telling you, those are all connected. The ions can flow from one cell to the other, create current that propagate in the tissue, creating a wave of electrical propagation. And that's what we simulated in computer models. This wave that travels from, for instance, left to right. But we're missing something. We need to actually understand what happens with mechanical forces. Let's give this stimulus to it. So this mechanical stimulus activate electrically the cells, and the effect of stretch-activated channels needs to be explored. So those cells start to produce the stretch-triggered action potential. They're still interconnected to the other cells, so this current still needs to propagate. But another stimulus was already there, so all the cells are colored. That means that they are really not ready to receive another stimulus. So the stretch-triggered wave wants to propagate, but finds a block. That means that actually this stretch-induced wave of activation is forced to travel around trying to overcome the obstacle, creating weird patterns of propagation that actually create something that's called re-entry. That's what we model in chapter 3 of the thesis. So those re-entries are really interesting to look at, but they are also very dangerous because they can create a perfect substrate for arrhythmias to develop in tissue. So in chapter 3, we found that the wrong combination of the same condition explored before in the cell model, so the stretch, the strength, the duration, and the timing, together with location, but also size of the mechanical impact, is able to trigger stretch-induced arrhythmias in tissue. And so, through the use of computer models, we were able to understand the underlying condition and the underlying mechanism related to the effect of stretch. And we found that indeed arrhythmias not only exist in space, but also in time. So, as a final question, we asked, what would happen with disease? So there exists specific disease called channelopathies that interest those ion channels. So for instance, fewer potassium ions can flow in one of those channels, and that will actually interest the action potential, which will be prolonged. But the other way around is also possible. So if more potassium ions flow in and out, they will actually shorten the action potential. So we try to model that in chapter 4, together with the mechanical impact and the stretch-activated channels. So the wrong combination of the same conditions, together with the disease condition, as I was explaining, exacerbate the stretch-induced arrhythmias, both in cell and in tissue. And again, through the use of computer models here, we found the underlying mechanism and distinguished between the mutations and those channelopathies. So to sum up, we, in this thesis, tried to bridge different worlds, from single cells to tissue to clinical application. And at the same time, we connected the mechanical and the electrical function of the heart, trying to rely on experimental data, overcoming the challenges using computer models. So stretching boundaries, and in this very complex but fascinating field of the electromechanical behavior of the heart. But the story is not over yet. So the mechanoelectrical behavior of the heart is still an open field with many other questions that we hope to answer in future. Thanks for the attention. I give the word back to the prorector.
Thank you for this clear summary of your thesis. The opposition will be opened by the chair of the Thesis Assessment Committee, Professor Paul Volders. He is Professor of Genetic Cardiology at Maastricht University. Professor Volders.
Thank you very much, Mr. Prorector. Dear Mrs. Candidate, congratulations. Of course, this is a topic to my heart, and I like it a lot. I think you did a great job. Really beautiful work, giving lots of new soil for hypotheses that need to be further investigated. And of course, I extend my congratulations to your supervisory team, Professor Lumens, Professor Heijman, Professor Delhaas. I think one of the most important questions I would like to discuss with you is the examples of stretch-related events in the heart as they can occur under normal conditions, or don't call them normal, but at least if they come forward for intrinsic reasons. So don't mention the word commotio cordis, because that's external. What could happen in the heart by which all of the work that you did shows to be so meaningful for our understanding of how the heart works, how arrhythmias come about, and also how it can be used in the clinic?
Highly esteemed opponent, thank you for your question. Thank you for your compliments. It's a really beautiful question because I think it's, so we try to model the extrinsic factor, obviously. So we really try to stretch over the physiological range. I think that's the key of the study. obviously, when it comes to intrinsic forces, we are talking about normal contraction of cardiomyocytes during the interbeat, normal beating of the heart. Surely, I believe that those stretch-activated channels are present and functioning also in a normal range of activity. So they should not provoke any arrhythmias in the normal behavior. So if data are given, obviously, it would be, we should be able to show that those channels function and those currents exist, but they don't lead to those events. So no triggered activity, and in the normal physiological behavior, everything should be in place. And I think that's about it. And then
Okay, so if I were to have a moment of stretch-activated impulse formation today, and you had to explain to your family what would be the mechanism, what could be conditions in the vivo heart by which these moments of abnormal stretch could happen?
So not about commotio cordis,
No?
but there can exist other pathological conditions, for instance, related to, well, surely there's long-term condition that could happen, so some disease that develop over time and creates remodeling, and therefore force those stretch-activated channels to function, and by time also functioning not in a normal range. But other example, if I may think about it, could be, for instance, mitral valve prolapse that can provoke stretching of the papillary muscle, but also arrhythmogenic cardiomyopathy or myocardial infarction as well. That
Absolutely. And so could it be as simple also as the single occurrence of an ectopic beat? Because if for one reason or another, for instance, well, you stand here and the stress levels may be a little bit higher than normal and your autonomic system is on, and for that reason there may be, for autonomic reasons, ectopy, then by the ectopy itself, compensatory pauses happen, and that in itself for the next beat may actually rise the moment of contraction, and as such also the mechanical consequence of that. So maybe it's very good to discuss disease, but maybe it may be as simple as the extras that come with ectopic beats, or the irregularities that come with, in relation to that, for instance, with atrial fibrillation. Okay, disease of the heart, arrhythmia, etc. But that is a situation in which you could foresee that the impact of your work is very large, because there it may actually feed back to the normal activity of the heart, etc. Okay. I think that's nice. I think you shine here like a first lady in the ceremony, so that's really nice. The other question is about the definition. If you call stretch-activated arrhythmias triggered activity, then somehow this feels uncomfortable with the definition of triggered activity as it has been posed by some of our gurus from the past who relate triggered activity to the fact that there must be a preceding action potential related to the occurrence of after depolarizations and as such also triggered action potentials. Would you think we need a new definition, or would you still defend that the previous action potential should be there for you to evoke a stretch-activated potential?
So, as far as understood, you're saying that previous action potential should be present to therefore evoke.
According to the previous definition, yes. But we can change it today.
No, I don't think I would like to change it. But I think that could be misleading saying stretch-triggered activities in a way that we observe the effect of stretch, and therefore the activation it's only electrical, and that will have produce this new action potential there. But it's enough. Previous action potential is needed in the sense that we need to be in the right moment in time to therefore have this impact, which will translate into an electrical activation.
Okay. So if you would have a long silence in the pausing of the heart, which sometimes happens, sometimes you get recordings of patients which fall still for seconds. I've seen traces for 20 seconds. And imagine such a trace happens. Obviously, that doesn't take long because otherwise the person will die. But in that 20 seconds, if you give a bump to the heart, and that evokes a new action potential, which often is actually done in the clinic just to get the heart going again, would you still call that triggered activity?
I think so, in the sense that if an external force is given, that will trigger something new. So I would still say that. Well, obviously it's so if there's a gap, the cells are recovered to receive this new trigger, but the other condition needs to be met of the trigger, so they need to be strong enough, let's say, to elevate the resting membrane potential and provoke the activation. I would still call it trigger. Mm-hmm. Maybe it's something that maybe it's too big of a word.
Okay, and then we may actually discuss it over a cup of coffee later and maybe come to a new definition. Thank you. I give the word back to the pro-rector.
Thank you, Professor Volders. The next opponent is Professor Alex Quinn. He's not here, but he's online, present as you see on the screen. He's Professor of Biomedical Engineering at Dalhousie University in Canada, so it's for him in the middle of the night. Professor Quinn, the floor is yours.
Thank you, Pro-Rector, and I think early morning at this point. Ms. Candidate, I'm very sorry I'm not there in person. I would like to have been able to celebrate with you here or there, but I'm glad that we have this technology that allows me to join you. Thank you for the opportunity to read your thesis. From the art at the beginning, which I much appreciated, to the entire document, I really enjoyed it. I want to ask you some seemingly maybe simple questions, but as primarily an experimentalist first, who has great interest in mechanoelectric feedback, there's some questions that have always seemed to be bouncing around the field and have always on my mind, so that's what I would like to talk to you about. So you, since the time of Fred Sachs, we've talked about this cation non-specific stretch-activated channel. And you evoke it in your modeling, as people do, and experimentally we talk about it. But what always has sort of amazed me is that one thing we're very good at now is identifying molecular candidates for channels. And you, excuse me. But yet we don't, for this channel, we do not have a candidate yet. And different channels are evoked sometimes. So do you think there is a cation non-specific stretch-activated channel?
Hi, esteemed opponent. Thank you for your question and for the compliments. Obviously, I'm not in the field of experimental, but I've been having, I enjoyed reading all those discussions about those molecular candidates. So, for instance, for the non-selective, it's always been said that those transient receptor potential channels could be the ones. Maybe there's many that together contribute and they are actually specific. We don't know yet, and I don't think I have a strong opinion on that. Obviously, in the model, we model that as a single channel that's non-selective. But maybe it's a combination of selective channels that creates that. And I think it's, experiment will tell, and I really hope there will be so that we can model that.
Some people would claim that all channels are mechanosensitive. So you talked about mechanoactivated or stretch-activated channels, but there's also the potential for mechanosensitivity of all of the channels that we think about. And one nice thing about the model is integrative, and so you could think that it's a combination of all of these mechanosensitivities that create a current that we attribute to a channel, but it's really a stretch current or even sensitive current because it may be modulating the activity of channels that are there. Do you think that would be important for modelers to incorporate and appreciate in their models, or do you think the way that we do it with this single channel is good enough?
Sure thing. I think more data are always useful. So we would be able to therefore really so I think the general result will not probably change much because it's a very strong effect. but the details, the tiny, teeny details will change if more channels are available to be modeled. And so we could really reach from a pool of different data to highlight the differences that they might come into play when it comes to, for instance, signaling processes. So if we want to go subcellular, they might actually be more important in this sense because they will strengthen the bottom, let's say, approach. So the end result probably will not change much, but the starting phase will do, because now we could model that from another perspective, from subcellular perspective. And that's probably when I think it's more important to have those.
That perfectly leads into my next question about minute details. Another thing that you included, which people do in computational models, is a potassium channel as well, potassium-specific channel, which, of course, would only cause repolarization if activated, not triggered events, as Dr. Volders talked about. So is that important to include? I mean, what did it do in your model? We include these multiple stretch-activated channels, yet the cation non-specific channel explains everything that we've ever seen experimentally, pretty much. So why do we include these other channels in our models?
Well, I still think that they are important to include to have the full picture. Obviously, the other channel effects are stronger than the potassium effect in obviously leading to after depolarization, triggered activities, because it's not what potassium does, but probably stretching it for longer time, that's where potassium come in handy. And also when modeling disease conditions, so for instance in the channelopathies, the presence of potassium in the stretch-activated channels could also be an important element to have there. So I would still keep it because there's many mechanisms that one can explore related to the potassium. But if we focus on the merely elevated, the action potential triggered by that, then that is less relevant. But I still would think it needs to be in there.
Yeah, that's good. That would be inclusive. So the last, or like maybe probably the last thing I'll get to ask you about, and this is something that also always, interests me, is you mentioned throughout your thesis often you use the word tension, and you talk about the tension in the muscle and you're evoking what the mechanical sensation that the myocytes or the myocardium is experiencing. But in your model, you model strain or stretch, right? And so what is the important thing there? Is it tension or stress, or is it stretch and strain, or strain and stretch? What do these channels sense? What is important for the effects that you saw in your models and we see experimentally? Is it stretch or strain that matters?
Well, I think I don't use the
sorry,
word...
stress or strain, sorry.
Yeah. Well, when I refer to stretch, I probably refer every time to the strong impact. So that really is able to stretch the cardiomyocyte. Maybe when it comes to stress, it's more of a physiological thing that one can envision in a bigger, so in the full heart. So I don't make this distinction in the thesis per se. I think it's obvious that they are interconnected, because if we have the stretch of the cell, that will therefore feed back into the heart and create more tension, and it's more of a process that works hand in hand. So they're both important, and we came to model the stretch, and actually not even the stretch, because what I model in the model is the effect of that, because it's only electrical. So we really focused on the effect of what an external impact would do, or a force that comes from outside. So we do really focus on the electrophysiology mainly in the model.
In what situation? I agree that you have stretch, you will have stress, right? Or strain, they go together. But in what situations might that relationships be altered or decoupled or change at least? When would we see a change in that?
Well, probably when the stretch is too strong to really find so that the heart doesn't function properly anymore. That might be the leading compare. So this balance can be unbalanced in a way. So I think when an external force is it's so strong and so powerful to disrupt the normal heart rhythm, then I still think that stress is related though in this behavior. So I'm not sure if I can think of a situation when those are really not connected, if not disease conditions, where the stress in the heart is not maintained anymore, so involving also hemodynamics.
It seems that the connection is frozen. I propose that we move on to the next opponent. Thank you very much, Professor Quinn. The opposition will be continued by Dr. Viviane Timmerman. She's a professor of computational cardiac electrophysiology at the University of Freiburg in Germany. Professor Timmerman.
Thank you very much. Thank you for being here today. Dear candidate, I really enjoyed reading your thesis. Fantastic work from the illustration to quotes and obviously the text. I was wondering, you were talking about beat-to-beat mechanoelectric feedback in your thesis, and also in your introduction, you mentioned that in physiological conditions, mechanoelectric feedback is really important. However, in your simulations, you set all the stretch-activated currents to 0, and only when there's stretch, so we have disease, they were actually functioning and contributing. So how can you explain this difference?
Highly esteemed opponent, thank you for your question and for the compliments. True, correct. Those stretch-activated channels only function when there's a more stretch, so when it's higher than 1, the sarcomere extension ratio. I think that what we model is this pathological condition of stretch that really, that indeed activate those in already over the physiological range. So we try to also include contraction signals electrically to really take into account this beat-to-beat intrinsic mechanoelectric feedback by opening up those channels also when the contraction is present in a normal setting. And but obviously the model is not electromechanical, it's an electrical model. So having the full picture is hard to have, but at the same time we really tried in the chapter 2 to have the presence of a stretch that varies to really hint the contraction from an electrical perspective. And in that case, the channels were there, but they were not leading to those events showed when that contraction pattern was not present. So the results were slightly different and kind of evolved together with the contraction pattern. What I think is that one should be able to have this connection in a final model to really make it work also when it's physiological range, and those channels should be there, the currents should be there, but they should not be able to trigger or to provoke disaster, and then over a certain threshold also provoke activities. But we did focus on the second part, so on the disease, more of that.
But do you think there's a functioning of the stretch-activated currents during normal heart rhythm? So do they actually have a role during that?
I think so. They should open when contraction, so when there's some mechanical activation. To the extent of those channels opening, I'm not aware of, due to experimental paucity. But it would be super interesting to see the actual effect and the single characteristics of those channels that I think they should be able to open, because otherwise there wouldn't be the link between mechanical and electrical functioning of the heart. But I may be proven wrong by experimental, because I obviously don't do experiments. I rely on what's in there available, and I made up my mind to think that this should work, but I don't know the extent of them. Maybe there's very little current there. And indeed, when more stretch is present, there will be more there.
Thank you. So you were talking about mechanical and electrical stimulation. What do you think is the difference? I mean, when I look at your 2D or 3D illustrations, wave patterns look very similar between electrical spacing and mechanical. So do you think there's a real difference between those two?
So I think that we don't have the mechanical deformation of the tissue, for instance, in the simulation. And also the tissue is a 2D grid, so we are not able to have the full 3D organ. So re-entries, in my case, look similar because we are lacking the mechanical component of the deformation. And I do believe they would be different, but at that point, I think it would also be good to include the 3D organ, so to see really the wave pattern. But overall, I think that we try to show the maximum effect we could have. So presence of re-entry already established, and what would cause the differences, and indeed the difference between mechanical evoked and electrical evoked re-entry could be interesting to explore, but we do need a different setting, and it was not the case.
Okay, thank you. I have one final question. When I look at your action potential from the experiments, you saw in the end when it was prolonged a zigzagging without having a stochastic formulation. How can you explain the mechanism?
Sorry, can you repeat the question, please?
So you have a prolongation of the action potential in your chapter 2, and you see a little bit of a zigzagging, like going up and down of the prolonged plateau phase. So you don't have a stochastic formulation. How do you get this kind of behavior?
You may give a short answer, please.
Sure. I don't recall the zigzag pattern. Mm-hmm. So I think this was given by the stretch contraction pattern, probably, that caused that. But we can definitely discuss that later on.
Thank you. And I give my work back to the prorector. Thank you.
Thank you very much, Professor Timmerman. The next opponent is Professor Frits Prinsen. He is Professor of Electromechanics of the Heart at Maastricht University. Professor Prinsen.
Thank you, Mr. Prorector. Dear candidate, I read your thesis with a lot of pleasure. The matter, the question of the mechano-electrical feedback is, of course, also close to my heart, literally, and also in terms of research, because I usually come from the excitation-contraction coupling, but I think this is a very important topic. I congratulate your supervising team, and you have excellent supervisors. They say that as a candidate, you're standing on the shoulders of your supervisors. Well, you managed to stand with 2 feet on the shoulders of 3 supervisors. So I think that's a great job. But I'm here also to ask some questions, to celebrate that. And I like to zoom out a little bit more even than the previous speaker. Because, and I hope nobody in the audience is getting in trouble with seeing all these terrible things your stretch-activated channel can do. This is a horrible thing. But the stretch-activated channel, whether they're separate or not, it doesn't matter. There's something there which came through by evolution. And evolution leads to the most fittest condition of the heart and of the body. So the stretch-activated channel must have a physiological positive role. Can you think of what that positive role could be? Because I think that is in 99.99% of the cases, that's the role that is important.
Well, Well, highly esteemed opponent, thank you for your question and for the compliments. Sure thing. We did focus a bit on the negative side of those stretch-activated channels, fair enough. And I do like the what you say about evolution. So they must be there for a reason. They must be functioning also in a positive way. I think they well maintain the balance between in the functioning of the heart. So they since we were talking about the mechanoelectric feedback strengthening the heart behavior such that contraction and relaxation go and trigger, the electrical activity as well. They must be there for feedback and to well maintain this balance, but also probably to, when stress condition happen to the person and or other...
Yeah, but you're not very specific now what you mean with feedback sounds great, but can you be more specific where those channels may play a role? And I have an example, and if you think of me, you know what I'm doing, so maybe it's a hint.
Well, I'm thinking of something very positive that could be the precordial thump when it comes to the heart being stopped, and therefore if...
No, the connection was lost. So,
okay, sorry. So if the heart, so one could induce a mechanical activation, and through this channel, the heart could start again beating. But that's a bit controversial, as far as I know.
But no, you know, I'm involved in work with ventricular pacing, and you have been exposed to that also in your own group. It creates large mechanical differences within the same heart. So this, and what we see is that if you have a certain period of ventricular pacing and then you go back to sinus rhythm, so normal activation, the T wave is abnormal. T wave memory it is called. And you can block the T wave memory development by giving a stress-activated channel blocker, whatever that is, or by just lowering the pressure in the ventricle. So, and that leads to synchronization of the repolarization, which is actually anti-arrhythmic. And so it's very funny that you come with pro-arrhythmic role, and so there must be a safety margin from good to bad. Like any drug, they have good effects and bad effects, and there's a safety margin. And so, and I was just trying to understand what it could be, and I have one question there specifically on your modeling conditions, which are shown on page 73 in your thesis, where you show the circular pattern, and so in that, the first in panel D, you have the first option is no gradient, which means that you have a circle, you have zero stretch here, and the next millimeter or even less, you stretch 30%. How can you do that even in this model? Because the cells are connected, because otherwise you don't get action potential conduction. Because if I stretch here, mechanically connected cells, there must always be a more gradual gradient of stretching of the cells. Or how did you do that?
So I agree with having a physiological gradient in the real heart. Obviously, we cannot do black or white. Because the cells are connected in the model, we could actually model the single cells and actually activate them electrically. If we were to stretch them mechanically, that would interest also the neighboring cell, but in a way this activation propagates as well on the neighboring cell around that. But we did force a gradient as well to really try to model more physiological activation of an area, so that's why the other gradients. So we were able to do a black or white situation. At the same time, with gap junction, the current was obviously traveling already in the neighboring cell, so we do see a little overlapping effect, but mainly since the stretch is very high in this case, in my model this 30% is very high, but let's not focus on the numbers per se, because I think it's that's a bit of a key here. Those numbers are very, if we...
Oh, I agree, 30%, that was my next thing, 30% is a lot. 20% is already much, but I think the spatial step you simulate is very strong, and I think it's great to show the mechanism, but from my perspective, I'm an optimist. I think that you sketch a very negative image, and I think the more realistic one is either the ring gradient or the point gradient, which is more the gradual thing. And that actually also explains why there's so many situations in life, like the pacing situation, like patients in atrial fibrillation with variable RR intervals, with the long compensatory pauses even. 99.9% of the patients survive that, or even more. So, but I agree, some patients have a problem there, but I'm just looking for more physiological balance there.
And I think that's also why I really wanted to model this more physiological gradient, I call it, and we didn't observe those re-entries in the same amount. We actually didn't observe any re-entry. We found positive, because that's what should happen in a normal behavior. So that would be really fade. So this hit will fade because the cells are connected and they really strengthen. So it's like a teamwork strengthening. And
okay, thank you very much. I give the word back to the pro-rector.
Thank you very much, Professor Prinsen. The next opponent is Dr. Matthijs Kluitmans. He is Assistant Professor of Cardiology at Maastricht University.
Thank you, Mr. Pro-Rector. Dear candidate, congratulations. Beautiful work, both content-wise and visually. I really appreciate also that you included stretch, not literally in the title, but also artistically. Actually, it took a little while for me to realize that, and I think that's beautiful. Congratulations to the supervisory team as well, who've contributed a lot as well, of course. I want to continue a little bit in the same direction of the previous discussion, but then in the context of myocardial infarction. So obviously a heart with scar, where stretch and strain are going to be different as well. And scar obviously means no conduction. Perhaps I should leave out the word obviously, because there is discussion about that. But let's assume there's no conduction, but it also results in abnormal stretch, which can have various effects. One of them, unconduction. You refer to a study where we, with a PhD student from Eindhoven, studied that. But then, of course, you add a lot of the stretch-activated findings that you have on top of that. So let's think a little bit about how your stretch-activated channel work would be situated in a heart with scar. For example, can you think about a way how scar, in using your findings, would result in premature beats resulting from the border between scar and healthy tissue?
Well, highly esteemed opponent, thank you for the compliments and for the question. I really resonated with the study because I could really link that to my work in a nice way, I think. And it's so the borders I show in the 2D simulation could already be, in a way, scar tissue, because we are modeling a 2D grid, so we are not modeling a 3D setting. So in that case, more borders and scar tissue could be present, both of them. We made a decision to not include areas where no conduction was. We didn't include other areas where there was no conduction. That's because we had already those borders. So, for instance, the really corner border could already induce some reentrant patterns in this natural way. Obviously, also having scar tissue will have an effect on the reentrant activity and on my results as well. And I think it would be interesting to observe that, but I would rather do that in a 3D setting where more tools are available, and one could really see how this wave propagates, in which way both the scar and the bone.
Okay, so let's do that, at least in our minds. So how would you study mainly the induction of premature beats? So not necessarily the initiation of reentry, but really the trigger, using not the findings that I just mentioned, but also your findings. So in other words, the work that we did in Eindhoven, how do we need to incorporate your work and to study if we can find stretch-induced PVCs?
So having the stretch-activated channels in the model already present in all the tissue and also in the scar tissue, but if we assume that there's no conduction, I don't think they would play a role in the scar tissue per se, because there's no conduction, so the wave cannot arrive. If premature beat happen, and as well there's an external forces activated those channels, those two waves could collide and create other patterns, and depending on the relative size of the refractory period, but also on the activation path, they will interfere, and that would be indeed many scenarios can be there. So they could create an S1, S2 protocol such that those both the electrically activated premature beat and the stretch activated current will interfere.
So are you saying that we still need to artificially create that premature beat because your stretch activated channels do not necessarily result in that in this condition?
Well, if paced activation is already present, that will create already that relationship where we probably don't need the premature beat. It depends on what we want to model, because in a way they will the stretch-induced activity will create a new beat happening.
Okay. Great, thank you. And I think you're already touching a little bit on repolarization as well, and stretch-activated channels impacting substrate, not just trigger formation. I want to move to art again. I think you like that. So when I was reading your thesis, there was also a very nice artistic project where people took algae that have bioluminescence, so they glow when being touched. So they're in the sea, and when there's a wave or when you walk through them, they glow up. So this actually appears to be stretch-activated channels as well. And what I did next was to make a dress out of that. So you could have stood here with a dress made of stretch-activated channels. Let's assume you would have chosen that. What could you do to give a live demonstration here and create re-entry with such a dress?
You may give a short answer, please.
I would need both somebody poking me and I should be talking on doing something myself, and on top of that somebody should just come and knock on my shoulder, and that would probably result in a re-entry myself.
Thank you.
Thanks.
I give the word back to the pro-rector.
Thank you, Dr. Kluitmans. The sixth and last opponent is Dr. Bastiaan Buikens. He is Associate Professor of Physiology at Maastricht University. Dr. Buikens.
Well, first of all, congratulations also with this beautiful thesis. I find it exceptionally clearly written. So my compliments to that, also compliments to your supervising team. But having said that, I would also like to discuss parts of the content of your thesis. And I would like to start at page 69. And I was wondering whether you would like to read first 3 or 4 sentences.
Highly esteemed opponent, thank you for the question. Sorry, can you repeat where?
So that will be chapter 3, and then on page 69, 69. It starts with reference to Garni and Cole.
Okay. Or also potassium selective sac helped highlight that stretch can lead to ectopic excitation in fully repolarized tissue, consequently interfering with the propagation of the normal electrical excitation, triggering conduction blocks and promoting re-entry mediated maintenance of ventricular arrhythmias.
All right, thank you. Thank you. So I was triggered by the term fully repolarized tissue. And if I think about fully repolarized tissue in a cardiac cycle, then I think at the TQ interval, when the whole ventricle is repolarized. And if ventricular primitive beats occur in this area, it's actually quite benign. And if a ventricular premature beat occurs quite close to the next QRS complex, it's also not really a problem. You can see that in patients with WPW syndrome. They have an ectopic excitation somewhere in the ventricle, and it collides with the next activation wave. So I was wondering, I don't really understand how that can lead to re-entry and to arrhythmia. So I was wondering, could you explain that to me?
Well, so highly esteemed opponent, thank you for your question and for the compliment. So, well, I do say that I trigger conduction blocks. So that's probably what can happen if a subsequent beat is happening right after. How that can promote re-entry is because that creates a substrate where there's no conduction happening, there's no activity happening, and that's probably where the substrate, if another, for instance, paced activation comes, the tissue would not be fully ready yet to.
So maybe if you go to page 83, and there you have figure 3.7, I think then you simulate exactly what you were just explaining. Do you agree with that?
I do agree,
yeah. And what you actually can see is that if you create a premature beat when repolarization is at half of your tissue slab, then conduction can go one way but not the other, because the other part is still refractory. And then you have the substrate of re-entry. So I would think that in the next thesis you will write, if you would adjust these sentences to say that in not fully repolarized tissue, but partly repolarized tissue, then you will have the substrate that could lead to re-entry. And actually the adjacent excitation wave is not at all necessary to explain that. Would you agree with that?
I do agree. I do agree, and I think it's really the combination. So the refractory area is interfering with the non-refractory area, and that's the ratio of that, the key for that substrate indeed.
Thank you. And I think I have a few minutes left, so I would want to continue on the re-entry. So if you go to chapter 2, to your graphical abstract, then you talk about the triggers. So I have to, am I already there yet? So I think it's page 25. And then you mention trigger activity as the mechanism of how stretch could lead to a trigger. And I was wondering, so if you apply pressure to myocardium, it will depolarize a little bit, and thereby refractoriness will increase, post-repolarization refractoriness, because the sodium channels take longer to recover from inactivation. And I think that could also lead to re-entry as a trigger. And I was wondering, do you agree with that? Do you think re-entry could also be a mechanism underlying a trigger when you talk about stretch activated?
Sorry, did you say trigger or treatment?
Trigger. So that it's a substance that if a premature beat due to the stretch activated channels occurs in a substrate, then you can get re-entry. But then the re-entry is the maintenance. And I was wondering, can re-entry also be the trigger?
I think so, because but then we are talking about a re-entry already established in the tissue. If that will be the trigger for a new beat happening.
Yeah. It would be maybe interesting to simulate once.
Well, definitely, if we look at a cellular perspective of re-entry, we do see a pattern of triggered action potential, but they are triggered in a way that they're they're not paced, so they do not happen regularly, so they're very disorganized. And in a way, they would lead to a beat happening, so also mechanically, that will create this irregular beating of the heart. But if they can restore and maintain the normal heartbeat, that we always need the normal paced beat happening on top of that to restore and take the lead of the reentrant activity present in the tissue.
Okay. I think that's a good answer. I have to think a little bit about it. But I see that I have time for another question, because the pedal is not here yet. And I was wondering, so the autonomic nervous system. So I think recent research has shown that there is a intrinsic cardiac nervous system. And I was wondering, could that also be responsible for the exopotential duration changes you see during stretch?
I think so. They must be related. From a pathological perspective, having also the stretch on top of that, that will exacerbate this effect. But I think they must be related, and really interesting also to have that signaling present in the model. That would be another nice connection to how the body actually works and maintains normal rhythm, tries to at least get back to that or not.
Yeah. No, I would be really interested in seeing those.
I really would also be, yes.
Mrs. Buonocunto, you have heard and seen that the time for defending your thesis has passed. The committee will now withdraw to discuss the quality of your thesis and in particular the quality of your defense, and please await our return here. Mrs. Buonocunto, the degree committee here present has assessed the quality of your thesis and also, in particular, the quality of your defense. And in view of this positive verdict and taking into account the previous examinations that have been done by you, the committee has decided to grant you the degree of doctor. And Professor Lumens is authorized to confer upon you this academic distinction in accordance with Dutch university custom and law. I give the word to your supervisor, Professor Lumens.
Ready? Do you promise to work in accordance with the principles of scientific integrity at all times, to be careful and honest, transparent, independent, and responsible?
Yes, I promise.
By the authority vested in us by law and in conformity with the decision of the committee here present, I hereby confer upon you, Melania Buonocunto, the degree of doctor and grant you all rights attached by custom and law. As evidence of this, I now present you with a degree certificate signed by the rector, the secretary, and the other members of the committee, and affixed with the official seal of the university. That's a lot. Dr. Melania Buonocunto. What an honor to congratulate you today here together with Tamo and Jordi, and to congratulate also Mattia and your parents and family and everyone who traveled from a lot of places, but also from Italy or elsewhere to share this moment with you, with us. Before I continue with my laudatio, I would like to use this moment to thank the members of the assessment committee, also online. Dr. Quinn, thank you. And Dr. Vivian Timmerman from Freiburg, thank you very much for coming all the way here from so far and spending your time, and also the other members from Maastricht and surroundings. Thank you. Well, October 2020, do you still remember?
Yes.
That was a rough time. The world was in a lockdown and uncertain, anxious. And you, Melania, you decided to leave behind the heat of Campania and your beloved Mattia and friends and family to start a PhD in a city you'd never seen, I think, and with people you'd never seen. That takes courage. That really takes courage. And Mattia and Papa and Mama, you two had the courage to let her go. To let her go to an unknown, and well, look here, look at her. Here she's standing. That's the result also of your courage. So you should be proud. So what also takes courage is working with a team of 4 supervisors, 4 personalities, 4 ways of thinking, 4 sets of expectations. And making that work, making chocolate from it, as we say in Dutch, requires patience, diplomacy, and resilience. And just when you figured out the recipe, the team changed. Aurore, she's in the room in the middle there. She's hiding a little bit, I know. But, Aurore moved on, and Jordi actually relocated to Graz. That's not, I mean, that's quite something, huh? Yet you adapted and you kept going. It made you a more independent person, for sure, Melania. Well, I touched upon Aurore. You were crucial in the early years, huh? And I'm sure you will agree on that. And you helped Melania navigate the complexities of our team, huh? In many ways, and you taught her to find her voice. That's really what you did to me, and that's to stand on her own feet. And by the time you left, then you were ready, and thank you for that, Aurore. Tammo, your endless drive for linguistic and academic perfection have really stretched Melania. I've witnessed that, for sure, but thanks a lot for that, certainly in the later phase of Melania's PhD journey. Melania, I know you felt that stretch, and with stretch comes also stress, yes, but you managed to control that, and you persevered and brought it to this result. Then Jordi, you became really Melania's compass throughout the years. She also very nicely writes about that in the Laudatio, and when she needed guidance on electrophysiology, arrhythmia, and navigating her research and life, you were there, stable, knowledgeable, and supportive, even after moving to Graz, of course. And now you remained her mentor. So I also want to thank, not present here, I think, but Katja and Nicolo from Bern, because you did a great job with them, and they really made a very nice chapter with you, which we are very thankful for. Melania, watching you grow these past years has been remarkable. You arrived cautious, always checking many things, sending me WhatsApp messages, being a bit insecure in the beginning, but always making sure you had permission for things. And I remember when you wanted to join also Jordi's and Paul's meetings, the team lab meetings, instead of ours, you really came to ask to me if that was okay. And I felt that you were a bit anxious for my answer. But I'm sure also there, Aurore really supported you and made you take that step. And today, I don't think you need that cautiousness anymore. You've discovered your own judgment and your own voice. Stretching boundaries, a super fitting title of your thesis. You stretched our understanding of SACs, let's say, stretch-activated channels, and revealing how mechanical forces trigger arrhythmia. But Melania, let's be honest, sometimes you stretch things a bit too far. Think about your knee injury with volleyball, that prevented you also from coming back to the Maastricht at a certain point. I think I remember. The Highland Games, do you remember those ones? Yeah, a bit too much stretch there. And there was, by the way, the sheep herding.
Oh, yeah.
I think many of our colleagues still remember that event, but also you during the sheep herding, and I won't elaborate. But let's just say we saw a side of you that they very competitive, very determined, perhaps a bit reckless as well. And your friends here know probably what I mean. You stretched me too, I must admit. My expertise is really in cardiac mechanics and hemodynamics, as you know. But your work pulled me into electromechanics, into electrophysiology, and I had to learn to grow. I don't know if I managed, but thankfully I could lean on Aurore and Jordi for the EP, but you and your work really challenged me. So here's what strikes me most, Melania, about you, is you'll probably credit for this today everyone else for getting you to this point. You'll say it was your supervisors, your collaborators, your family, Mattia. And yes, they helped, really, they did. But this is an achievement, this is yours. You did the work. You persevered when things got difficult, when doubts crept in, and they did at certain points. And look at you now. You're standing here with a doctoral title, and that's yours forever. You've become an outstanding scientist and a remarkable person. Now we go celebrate. You go celebrate with Mattia and everyone who loves you, and I'll join you on that, of course. You've earned every bit of this, and I wish you, Mattia, your family, the brightest future. Stammi bene.
Thank you, everybody. Quite speechless.
I want to say something to you. Esteemed Dr. Buonocunto, dear Melania, it's a great pleasure for me to congratulate you with your doctorate, and I congratulate you also on behalf of Maastricht University. But not only that, I would like to share some impressions from the committee with you. First of all, I would like to compliment you with a fantastic, what we call a layman presentation. So the summary of your thesis was extremely clear, very beautifully illustrated, and it is meant for non-experts. And I hope and I think that many people here in the aula and also of the followers of the live stream understand more or less what you have done the last couple of years. And Maastricht University thinks it's very important to bring results of scientists into the outside world and to make clear what these people are doing, why they do that, and what does come out, and what is the consequence of these findings. And you did that wonderfully well. With respect to your thesis, it was for the committee easy to read. It was very well written. It was also focused on an interesting and relevant subject. And the scientific studies were excellent, were very well done, and the scientific results matter. With respect to your defense, we realized that the committee had a variety of questions also beyond the borders of your thesis. And you managed well. We are aware that it's difficult to answer and to react and to respond and to defend to all these questions. But you did very well, and we are very satisfied. And we have seen also that you are very well able and knowledgeable in the field that you have studied. I do not only compliment you with that, but also your three supervisors, Professor Joost Lumens, Professor Jordi Heijman, and Professor Tammo Delhaas. Congratulations with the results that we all have seen today here. And of course, I would like to include in my congratulations your family, from the lively and beautiful city of Napoli all the way to the Netherlands. Congratulations, and I also not only want to congratulate your family, but also your partner. And nice that you were able to come over here to see this and to enjoy this. Congratulations also to the audience here in the aula and also the audience and followers of the live stream. And I'm sure that quite some of your acquaintances, of your colleagues, your former colleagues and other people have watched you acting today. I would like to thank all the members of both committees, not only this committee, but also the assessment committee, the thesis assessment committee. Thank you very, very much. And I would like to say a special thank to the external members, like Professor Lumens already did. Professor Alex Quinn, thank you very much for joining the committee here. And I would like to give you the word to congratulate the young doctor.
Thank you very much for the opportunity. Dr. congratulations. I don't know what to say much after following those, both very nice summaries, but I will reiterate that this is a great accomplishment, something that you should be very proud of, and it was a beautiful piece of work, and I've seen it actually as it's gone along, not just in the thesis, but having seen your papers and such before even seeing your thesis. It's been nice to see your progression from afar. I just wish I was there to congratulate you in person. But enjoy today and the feeling that it gives, and also to your family and your loved ones and your friends that are there and your supervisors. It's an accomplishment for all of you, but really, I think as you said nicely, you can give them all credit, but it's really your credit to where you've gotten to. So congratulations, and I look forward to, I hope, at some point, getting a chance to talk about this in person in the future.
Thank you, Professor Quinn, and thank you for being with us in the middle of the night. I also would like to thank Professor Timmerman for being here and joining the committee as an external member. I have one way of order to tell you. I would like to invite you for the reception, which is in the rafter. You find that easily. If I have closed the ceremony, I would like to invite you for the reception in the rafter, which you find easily by going out here to the left and then around the elevator, go to the right. We make, after the ceremony here, a picture with you in the middle here, and I would like to invite the close family to stay here, because we do not only make a picture here with Professor Quinn on the screen, but also in the hall we make another picture. Hereby I close this academic ceremony.